than motion. So yesterday we talked about velocity, position, acceleration, all of those things, and really talking about mainly a particle moving. But we can apply rates to anything. To know if something is increasing or decreasing, you are going to check the rate of change. And the rate of change is just a derivative. The derivative is going to tell you the instantaneous rate of change. So the rate of change at one specific number. All right, so you're going to see this new kind of notation. You're going to see the dt. So if height is increasing, the derivative is going to be positive. And so the way that I'm going to write the derivative of height in terms of time is dh dt. All right, so the derivative of height in terms of time, and if it's increasing, then that guy here is going to just be positive. All right, so if velocity is decreasing, we're going to write that the same way, dv dt. What else does the derivative of velocity tell us? Acceleration. So this is also going to be a of t. And if it's decreasing, it's going to be negative. So dv dt and a of t are the same thing. It is the derivative in terms of time. So my variable is a t in my functions. All right, Miss Stahl's IQ is increasing. So dq dt is going to be greater than 0. So basically, if anything is changing, which in real life, everything changes, you can find the rate of change in terms of time. And I already talked about this, but derivative tells you the instantaneous rate of change. Instantaneous rate of change. All right, now on a lot of your homework for tonight, it gives you, if you look at the paper, there's a lot of words on it because it's kind of a real life scenario, but I would say like 70% of it can be done in the calculator. All right, so a lot of the questions are calculator questions, and I think I try to put like calculator on the ones that are for sure calculator to remind you to use a calculator. So as a refresher, if I want to figure out what the derivative of at 3 is, and it gives me f of x equals 5 sine of x, I'm going to go in the calculator and I'm going to hit math 8, and it's going to give me this ddx thing with some parentheses and x equals at the end. In the parentheses, you put the function that you're wanting to take the derivative of. You are not taking the derivative by hand. We're letting the calculator do all the work. So we are going to type in the exact function, and you're going to make it x equals 3. And so the calculator will take the derivative and plug in 3 for you. And it's going to give you negative 1.999. All right, so under your calculator steps here, I'm going to put math 8, which looks like n deriv. All right, so on example 15, it says if f of x is the bunny population after x years, then what is f prime of x and what are the units? All right, so I want to know the units. So f of x is the bunny population. So the units for f of x is going to be number of bunnies. All right, f of x is the bunny population. That's how many bunnies there are in my scenario. F prime of x is going to be the rate of change of the number of bunnies. All right, so this is the rate of change of the number of bunnies. So your units are going to be bunnies per year. Anytime it's a rate of change, it's something per something. All right, so this is kind of going back to that very first lesson that we did. So on 16, if f of x is the rate at which the bunny population increases in bunnies per year, then what is f prime of x and what are the units? All right, so on this one, f of x is already a rate of change. So f of x in example 16 is the rate of change of the number of bunnies in bunnies per year. It's art and they play music so loud, but it's okay. All right, so it's the rate of change of the number of bunnies in bunnies per year. All right, so when you're doing the derivative is another rate of change. This is a double rate of change. It's a double derivative. So this is going to be the rate of change of the rate of the number bunnies. The rate of change of, oh wait, I lost rate. What happened to my rate word? The rate of change of the rate of the number of bunnies increases. I feel like that English is bad. That the rate of change, that the rate of the number of bunnies increases. Does that sound better?
Let's just
Keep it as of? Okay, whatever.
It's just getting confusing.
Why is there so much writing for such little of a
I know.
So are we gonna have to do second derivatives for these?
No.
What do you mean?
Like
Rate of change,
prime of x.
Oh, no. You're not going to have to do like the rate of change of the rate of change of the rate of change. You won't have that. It'll always just be, it'll be either one rate of change or two rates of change. Yeah, no. What are the units for the rate of change of a rate of change? Yes. It's the acceleration. I don't know. A farmer. Okay. On 17, this is also kind of bringing it back to some old stuff, but it kind of applies to these real life scenarios because you're going to see these questions on the real life problems. It's going to give you a lot of words, and then it's going to say something like estimate p prime of 15. And all it's given me is this table. All right. And what a lot of people see is they see p prime and they want to have a function that they can take a derivative of. All right. But I don't have a function that I can take a derivative of. All I have is a table. So how can I estimate the derivative? A-Rod, yeah. Rise over run, slope, right? So if you're estimating a derivative, you are doing A-Rod. And what 2 points am I going to use? 10 and 20. Yeah, because you want to get as close to 15 as possible. So then you're going to go 150 minus 120 over 20 minus 10. You do not have to simplify, but you do need units. So if you leave your answer like this, you probably are going to lose a point for units. And if you want to simplify, you can. It does simplify down to a nice number 3. What would my units be for an estimation of the derivative? People per year. So think about what the units on top stand for. 150 and 120 stand for people, and 20 and 10 stand for years. So it's people over years. All right, estimate p prime of 20. Now, I don't think you see this very often, but I at least wanted to talk about it once. If you are trying to estimate the derivative at 20, you either want to use 10 and 20 or 20 and 30. You want to get as close to 20 as possible. So it's kind of like a 2-answer possibility. You could either go 150 minus 120 over 20 minus 10, which is what we just did, 3 people per year. Or you can do the 20 and the 30 and do 200 minus 150 over 30 minus 20, which is going to give you 5 people per year.
So on the AP test, are they looking for units?
Yes, they'll look for, if it's a real life scenario, they'll look for units.
Okay, so we should always like not abbreviate. We should just put like people, years.
Abbreviate how?
Like as in, to be safe, we should like type out or like.
You mean like P over Y?
No, like just spell out people instead of like PL.
Oh no, if you put PPL, they'd be okay with that. And years is YR.
So can we not use like local linearity or the thing where we use?
You could, but we don't know what the derivative at 20 is, which is where we're kind of stuck. So for local linearity, you need to have a number for the derivative to estimate. Does that make sense?
Why is it bad to do, like if you were trying to do like 20?
Like 10 to 30?
Yeah.
Because you want to get as close to 20 as possible. And so if you're doing from 10 to 30, it's a 20 year gap as opposed to a 10-year gap.
Yeah, I was just thinking, it kind of seems like you're trying to solve for 25.
Yeah.
But
And that's why I don't really feel like that question's asked very often, but just if it was, you should use 20 because you just want to get as close to 20 as possible. Okay. Lots of words. People are entering a building at a rate modeled by F of t, people per hour, and exiting a building at a rate modeled by G of t, people per hour, where t is measured in hours. The function f and g are non-negative and differentiable for all times t. Write an inequality that indicates that the rate of change of the number of people in the building is increasing at time t. All right. So, is this a common question? You're going to see lots of words. It's going to give you lots of information. And my advice for you is if you come across this and you're like, what? Is just to start to break it down. So, people are entering a building. So, I'm going to write, okay, people are going to enter, and that's F of t. And then people are going to exit, and that's G of t. Now, both of these guys are people per hour for their units. So units are important. And then it says t is measured in hours. Function f and g are non-negative and differentiable. So the non-negative just makes sense for, like you can't have a negative person enter the building. Does that make sense? That's what the exiting function is for. And then the differentiable just means that you can apply all of those theorems because differentiability implies what? Continuity. So if you had to do any of those theorems, you have to write differentiability implies continuity. And then next part here says write an inequality. So this is what it's asking for. The question is to write an inequality. What is an inequality?
less than.
Yeah, less than or a greater than sign. All right, so my end answer should have a less than or a greater than sign in it. And I want to write an inequality that indicates the rate of change, which are these two formulas right here because they're people per hours. So the rate of change of the number of people in the building is increasing at time t. So the number of people that are entering the building has to be what? Greater than.
That's not confusing.
What if it's a hospital and they're born there? So
We're not gonna get that. We're not gonna get that complicated in it.
That is a fair question.
We're gonna take the problem at face
There's a
value.
question on the AP test that says something about a hospital and people exiting. I get it wrong because it's flipped. So,
I think this was a former AP question on the test. I pulled that one. Like that was one of the parts, like ABC. So was this one, the gravel question. All right, so on a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by G of T, and it gives me G of T, where T is measured in hours from 0 to 8. At the beginning of the workday, the plant has 500 tons of unprocessed gravel. During the hours of operation from 0 to 8, the plant processes gravel at a constant rate of 100 tons per hour. Is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5? Show the work that leads to your answer. So it gives you a ton of information from the get-go, and you have to kind of break it down. So I've got, on a certain work day, unprocessed gravel arrives. So unprocessed arrives, and that is G of T. All right, and that the units are going to be tons per hour. All right, at T equals 0 at the beginning of the workday, you have 500 tons. You're starting with 500 tons of gravel. And during the hours of operation, you process gravel at a constant rate of 100 tons per hour. All right, so I want to know, is the amount of unprocessed gravel at the plant increasing or decreasing at T equals 5? So I need to write an expression for the amount of unprocessed gravel.
Plug it in, it's the calculator, the function, and plug in 5.
Okay, well, so I just want to know if the gravel, I just want to know, like, is my pile of gravel, am I making, like, is it going to get smaller or is it getting bigger? All right, so I'm going to take the processed gravel that arrives, because that's going to make my pile bigger, right? And I'm going to subtract how fast I process it, which is 100. Do I care about the 500? Do I care about how much I started with?
No, because that's not.
It's a constant.
Nope, it's just, yeah, it's a constant. So if you're talking about the derivative, what happens to your constant? It goes away. So I actually don't care about the constant because that's just how much I started with, but it has nothing to do with the rate that my gravel is changing at, because it's just how much it started with.
It even works in real life examples. That's cool.
Yes, I know. Like, calculus is so cool. All right, so this G of T arrives, and this is how fast I process. All right, so now that I got my, did I spell that wrong? It's fine. Now what do I do?
You attach a T to the 100.
Put everything that's in G of T.
But what am I plugging in for T? 5. So I'm going to plug it in. So in my calculator, this is a calculator question too. So we're going to plug 5 into my function. Which is going to give me 98.14, and then we're going to subtract 100 to it.
In this, you just plugged 5 into that whole entire top line.
Yes, so I plugged 5 into this guy right here.
Alright.
Not the derivative, because this is already tons per hour. So G of T is already, if you notice, your units right here are already matching. So you shouldn't be taking the derivative of G of T, which I think is what some people might have done on the AP test. So that's why writing down your units I think is helpful, because you're like, okay, units already match, we're good, I don't need a derivative. All I need to do is plug in 5 and look at my number. So when you plug in 5, I get 98.14 minus 100. So that's going to give you negative 1.86 tons per hour. So now we got to answer the question at T equals 5. Is the amount of unprocessed gravel increasing or decreasing? Decreasing. Why do we know it's decreasing?
Because
Yes, because your rate's negative.
okay, so we don't attach a T to the 100 because we're just talking about that precise moment. We don't care about what has happened before.
Right.
The derivative is rate.
Right.
Okay, that's cool.
Yeah, I'm understanding.
I have a question.
Mm-hmm.
So say like your units didn't match. You would just all you would do is find the derivative.
Mhm.
How does that affect your units?
So, hold on, let me finish writing. At t equals 5 decreases because
Negative.
rate is negative. Okay, so you're saying hypothetically if they gave you g of t and g of t was just the amount of
Yeah, just tons.
just tons. So then when you took the derivative of g of t, it would turn it into tons per hour
It's slope.
because it's slope. Yeah.
Okay.
But since this one is already a rate, this is already tons per hour, and then this is a constant rate of 100 tons per hour, my units match. I'm not doing the derivative. I'm not going to add a t. Like, we're good to go. Kind of make sense? A little bit? Okay. Why not? Rest of class, you have to work on your homework. A lot of it's calculator. Please don't try to take the derivative by hand because they'll give you, like, this function right here would be kind of gross to do by hand. I mean, it's possible for sure, but if we have a calculator, we want to use it. It'll save us time, and we can focus on, like, the words more and less on the straight math. Yes.